Okay, you should have host privileges now, and go ahead and wait until a few more people show up. You probably should have, based on class, you probably ought to have over 20 if they all show up.
Okay.
And just go through the plotting relatively slowly. Because all you have to do is illustrate plotting with those different data models, and good to go. So can everybody that's logged in right now see Josh's screen?
So
Okay, you got one yes, Josh, so I'm going to leave it to you. I'll be listening in for a while, but I'm going to leave a little bit earlier today.
Okay.
So when you get done, just terminate the Zoom meeting and it should automatically record.
all right, let's hope.
All right. See you in a bit. Bye.
Okay, bye. We'll wait for a couple more. Okay. There's always the recording. So let's go ahead and get started. So today is going to be a high participation lab, unless you want it to take forever, because we are going to be doing the process of approximating a plot given some data. So what do I mean by that? Well, here we've got some data right here. And what are we going to be doing with it? Well, we're going to be making a plot out of it, just like we've seen with scatter plots and just like you've been doing most of your lives with algebra. You've got, an X axis and a Y axis, and then you've got points on it. Something like this or whatever. Who knows where they are? And then given those plots, you can make a line that goes through them that is as good as you can get it. So the game we're going to be playing is given a couple different formula. How can we get this line to be as good as we can get? So here is our data. Got your X data here on the left and the Y data here on the right. It's not terribly important to know exactly where it comes from. The important part is to know what's the input and what's the output. Okay. So first thing we've got, this is going to be our function that actually plots stuff to the screen. Not super important. You know exactly how it works. We're just going to be using it a lot. Okay. Next thing is we're going to be using a couple different ways of writing or drawing a plot. So what does that mean? Well, the first one, we're going to be approximating what the line that could go through the points as a line. Trying to get the best line we can. And that's going to be y equals b0 plus b1 times x. Same thing as y equals mx plus b. It's just that b1 is m and b0 is b. The next thing we're going to try is quadratic. So we're going to have both an x and an x squared component. And then we're going to try with a power law, which is some constant plus x to the power of something. And then finally, this residue function, Well, I'll talk about it when we get to it. All right. So here's our data. We're going to store it into some lists. We got our X table for our input and our Y table for our output. First thing we're going to do is plot the data so we can see what it looks like. And I'm going to put something intentionally obtuse in here. Let's see. What did I, oops, did I not? I didn't run this cell. All right. So the red points are the actual points we have from our data. So 1.0 comes out as 1.0. 0 comes out as 0, so on and so forth. What the blue line is our approximation. So currently our approximation is not too super. I imagine we would want something that kind of went up in this area, and ours isn't really doing that. The perfect line would be able to go through every single point, but that is actually going to be kind of hard to do too, seeing as there's no way that a straight line can go through all of them. So that brings us to the question of how good is this line? Well, based on just looking at it, would you say that line is better or this line is better? The first one or the second one? Okay, you think the second one's better. Why would you say that? What makes you think the second one is better? It has contact with more points than the first. Sure, it actually intersects this point and this point. And this one down here only intersects this point. Because it has a closer slope. How can we say a slope is close? Well, here's what we can do. I can measure the distance, I can measure the distance between each point in red and each part of the blue line that lines up with it horizontally. Or sorry, vertically, just like this. So I'm going to measure the distance between these two. Now what I'm going to do is I'm going to add them all up. Each green line here is what is called a residual. It's the difference between the point we actually have and the line we currently approximate with. So with that in mind, what would the perfect line have for each residual? 0, correct. That means it intersects every single point. So that would mean that the closer we get to 0, the better it is. So we add all these up and we get a single number out of it. And that is what is called the residual. And we'll see that here. So this first number are the residuals for that line I have right here, the straight blue one. Now there's two numbers here. Now what's that about? Well, there's this method for calculating residuals that is called the sum of the squares. So rather than actually take each residual, we're going to square each residual so that they're all the same sign. It's like taking the absolute value. We're going to square them all and then add them up. And this method actually turns out to be a little more useful. Okay. So now that we've answered the question of what is, if we have two lines, which one's closer to what we want, by saying that the one with the smallest residual is closer, we can try what we want to try. So here's the question. We want to mess with B0 and B1 to get a closer line here. So can somebody give me a value for B0 that we want to try? There is homework, and I will only get to review it if we can get through the lab in a timely manner. So if nobody wants to participate, then we're not going to get to it. Unfortunately, we don't have an infinite amount of time. So what might be a B0 value that we can try? B0 is the intercept, the y-intercept, and B1 is the slope. Okay, so you want to try with 1? We can do that. And what's a B1 value you want to try with? So this will be the slope. Earlier, I entered a slope of 0, which is why it's flat, horizontal. Four? Okay, we can do that. All right, here's what we got. Now, how is this different from what we have above? Well, the line we had above looked like this, which means that it did two things. One, it moved up, and two, the slope went from like this to like this. Okay, so we changed two things at the same time. So maybe we should focus on changing one thing at a time. So we know that if we change the B0 value, it moves this part up or down. And we know if we change the B1 value, it moves the slope up or down. Okay, so let's ask the question, is this line better than the one we had before? Well, neither one of them are super great, but we can still calculate the residuals. Now this residual is huge. We want something smaller. All right, so this, we have two of them. The one we had before is closer, so we're going to stay with this one and try to change it somehow to get a little better. So let's try again. Now this time, let's only change one thing at a time. Should we move the B0 up or down, or shall we move the B1, which will change the slope? You want to change B1? Okay, so we'll set B0 to 0. What should we put in for B1? One? Okay, that's pretty good. All right, so here's what this plot looks like. Now, I would definitely say it's better than what we had with the 1 and 4. But do we think it's better than the one we have here? Visually, I think so. I think we'll get a better residual than we had up there. Look at that. We have got a much better residual, 0.09 versus 4.3. So this, what we have here, is much better than what we have here. Okay, so now we're going to keep doing this process. Let's do it again, because we want to get closer, right? So we had 0 and 1. Do we want to move it up and down at all? Or do we want to move the slope? Up and down? Okay, so that means we're going to change B0. So what do we want B0 to be? Now keep in mind, the scale here is not very big. So if you say to move it up 1, that means the line will go all the way up here. .05. All right, we can try that. That for B0 and 1 stays the same, or B1 stays the same. Okay, this also looks pretty good. Let's calculate the residuals here. 0.03. That is better than 0.09. So the natural question should come, how long am I going to do this? So what do you guys think? How long are we going to do this? How many times are we going to try to get a better line for our approximation? Until the residual doesn't get lower. Okay, that could take literally forever. And that's kind of the issue. That's kind of the thing I wanted you to think about, is we could keep doing this forever and ever. And that's what can happen with the computer too, which is why when you do this, you usually provide two things. One, a threshold on your residual that once you get below it, it's good enough. And two, a maximum number of tries to go through. So for our purposes, let's say if the residual gets below 0.05, we're good. And we won't do it more than 10 times. All right. So have we done it more than 10 times? No. Is our residual below 0.05? Yes, it is. So close enough. So 0.05 plus x is the slope we have here. And that's the one we're going to kind of go with for linear approximation. All right, let's try the same game, but this time we're going to use a quadratic approximation. Now, what the heck does that look like? It looks like this. Same data, but let me put it this way. 0, 0, 1. So this looks like an x squared kind of thing rather than something equals x. So it would go off in this direction if we let it. So we're going to do the same thing. But now we have about 3 variables we can mess with. Now, what do each of these do? Well, you tell me. Someone other than Carter or Carson, what does the B0 value do? By changing the B0, what does it change on my line? Or in this case, it's a curve. It's really not just a line. The intercept, yeah, it moves it up and down. Okay, so B0 moves it up and down. What does B1 do? Someone else. Yes, it's the slope. I was about to try to give a hint for it, but yeah, that's right. So what's the slope? Well, take the curve we have here. The slope changes the steepness of where it is. So the curve stays the same, but if I decrease the slope, then the curve would do something like this. Or if I increase the slope, it'll do something like this. And so what does the B2 value do? Well, actually what it does is it changes the curvature. If the curvature is 0, then it's just a line. If the curvature goes negative, then it goes like this. And the higher the value you get, the more acute it'll be. So with that in mind, what do we want to do? Well, let's compute first the residual. That's not super awesome. Let's go for 0.01. That'll be our tolerance, and we'll try it 10 times. So Carter says change B2 into -1. So the question I was going to ask, he just answered, is let's mess with the curvature, and we're going to make it negative. Okay, we can do that. So 0, 0, -1. Okay. So this changed our curvature. It flipped it completely, which is kind of what we wanted because it's curving the wrong way. But now we're running into an issue that it's going way down here, and the residual is pretty bad. So which of these 3 values do we want to mess with next? What do we want to do with this curve here? What's wrong with it? B1 needs changing, yes, because the slope is too far down. It's too negative. If we can make the slope kind of go up, it would make the curvature follow the pattern of the dots pretty nicely. So let's try doing that. Now, why are we only messing with one value at a time? Is because if I change more than one thing, it becomes difficult to tell what does what. So we're going to only mess with one at a time. So we're going to keep B0 as 0 and B2 as 1. All right. So 0. And what do we say we want to try with? So it was 0 before. What do we want to change B1 to? A 1. Okay. And then -1. All right. So this is better than what we had, I think. 2.8 versus 12.5. So definitely getting closer, but maybe not far enough. Who knows? The question you got to ask for the slope is the slope high enough or not? Because this could also be a case of the curve being too steep. Here, I'll show you what I mean. So I'm going to keep everything the same for B0 and B1. So 0, 1, and call it -0.8. So these are similar, but the curve is less. So now the question is, from here, do we want to mess with the slope or do we want to mess with the curve? I would say both need messing with, but which one do we want to mess with first? The curve? Okay. What shall we try? I kind of gave you a sneak preview that -0.8 won't be enough. So we have 0, 1, and what do we want to try? It needs to be negative. So it has to be somewhere between -1 and 0. -0.01. I think that might be a little far in the other direction, but let's find out. Okay. So the curve is barely there. So I think we need a little bit more of a curve, but it's closer, I think. We have 0.15 versus 2.8, so definitely closer. So what do we want to mess with now? The curvature or the slope? And this is the 4th time. So we got 6 more to try. If we can get below 0.01, then we're good. So do we want to change the curve or do we want to change the slope first? They both need to change. Curve? Okay. So we've tried -0.1, those two flat, and -0.8 is two curved. So let's pick something between those. What should we try? Ray says something entirely different. So let's see what it is. 0, 2, -1. Okay, now that has gone above the lines or the points. What's our residual? 0.07. So it is closer. That's cool. That's fine. But we're not quite where we need to be. So of these values, which do you think we want to change? Say the slope. So here's the thing about the slope, and I'm not saying you're wrong. If I change the slope, it changes this where it goes. And so the point of on the end will no longer be intersecting with the red dot. So maybe we might want to mess with the curve. Maybe, who knows? So if we're messing with the curve, we want it to be a little less curved. We want it to be a little more flat. So we want something closer to 0 than what we have. So let's try, I don't know. So 0 to -0.7. Oops, did I do the right one? No, I didn't do the right one. 0 to -0.9. All right. 0.14, 0.07. Okay, so let's try mess with the slope. 0. I don't know. What do you think? 1.5? 1.8? What's something we can get close with? 1.5? Sure, we can try that. And -1. Okay, that takes it down a little much. Let's try flattening this out. 0 and that. increase the slope. Almost where we want. So the closest one we've had was this one. We haven't got to the 0.01 that we wanted, but we did reach the 10 that we said we were going to stop on. So that's fine. We didn't get to the tolerance we wanted, but this is not bad. And when you are telling the computer what to do, it needs to know that after a certain number, which isn't going to be 10, it'll probably be like 1,000. Eventually you have to stop because you don't want it running forever. So we reached the number we wanted to go with, and this is the closest we got, which is not bad. 0.07, it's pretty good. All right, let's try another type of thing. This one, instead of y equals x or y equals x plus x squared, it is this one here. So y equals some value plus x to some power. So that's what we're going to try now. So let's do that. And we'll start with 0, 1, and 2. Okay, so this is what it looks like right now. We kind of have the same thing going on here. Slope, intercept, and curve. So what do we want to change? And we'll use the same values we had before. So 0.01 and 10 tries. Curve. Yep. And we need to flip it. And the thing is, you don't want to go negative. You want to go on the other side of 1. And what do I mean by that? I'll show you. So 0, 1. And instead of putting -2 or something, I'm going to say 0.5. And that will give us the flip that we want. Okay, so what's the residuals on this? 0.09. Okay. So what do we want to change here? Any of the three. And you can even put in just the 3 numbers if you want. I would say either the slope or the curve. Either one. Slope maybe. So it'll tilt it down, but we might get closer with these. So let's make the slope just teeny tiny smaller. So 0.8. I'll even go with 0.9 and 0.5. All right, so that moved it down just a teeny tiny bit. And we did get just a little, well, actually, as far as this is concerned, we got closer, about 50% closer. Okay, so that's something. Now, what do we want to change? Less curve. Okay, so that would be closer to 1. So we have 0.9 and we'll try 0.55. Okay, what's the residual here? 0.048. So we're getting closer. I'll even try something like 0.8.6. That might be a little far. It is a little far. 0.5.55. Okay, so the best one we've had so far was 0.9 and 0.55, right? All right. So let's give this one more try. Let's try just a little bit less curve. So 0.9, 0.58. We did get a little closer. And if we keep doing this process, we'll eventually get either to too many attempts or to the threshold we want. Okay. Now, what we want to do is what is called interpolation. Everything we've been doing so far is interpolation. So this process we're about to do is called interpolating polynomials. So polynomial interpolation. This is a verb. Oops. This is a verb. This is a noun. What have we been interpolating? What does it mean to interpolate? It means to go from one to the next. We've been interpolating polynomials this whole time. So the process we've been doing is what we want to tell the computer how to do. So let's do that. It's not important that you know what Lagrangian interpolation is. It's just a method that we know works. So we're going to build a function, and what it's going to do is it's going to interpolate until either we get to a threshold or we go by past too many steps. So we take the input and the output just like we had before. And this time, what we're going to also have is a predictor. What it's going to do is it's going to calculate the residuals just like we did, but we're going to put it inside of a loop. Why does your lab not have this part included? I don't know. He must have removed it, which is strange. That's okay. That would mean, okay. I'm just going to show you that if we take the process we've been doing and automate it, rather than just doing it forever ourselves, what we end up with. So if we keep doing the process, we would eventually get something so close where the residuals are, and this is the wrong code, are very, very small. Okay. So if that is the case, then we're actually done with the lab. This process is the same for each of these, and you're going to be doing the same thing in the homework. So does anyone have any questions on how this process goes? I'll try to summarize it a little bit. You've got some points, input, output, and you put them on a plot. The first thing you do is you choose a method that you want to put a line with, either linear, quadratic, power, whatever. Next thing you do is you choose something reasonable to start with. What's something reasonable to start with for a line? I don't know, I'd probably say 0 and 1. What's something reasonable to start with for our quadratic? I'd probably say 0, 1, and 2. This would be y equals 0 plus x squared. So the 0 is for the b, the 1 is for the x, in front of the x, and this is x squared. And then you just keep changing one value at a time until you get where you want to go. So let's look at the homework. You've got input and output, just like we had. They come from different sources because it's a different problem, but you're not really concerned with what the problem is. You're mostly concerned with getting a plot for the input and output. So x versus y. All right, what are we going to do? Ignore this part. You want to plot this with time on the horizontal axis, which will be the independent, the x-axis, and mass on the vertical axis. Use red circles as the marker. Create and plot a linear data model using a blue curve for the model. So you see the equations here. This is the same thing as y equals b0 plus b1x. Create a list of prediction error and produce a histogram of these errors. This is the residuals. Compute the sum of the squares of all the residuals. So that's what I was talking about with using the squares rather than just adding them all up. And you've got your scaffolding for what you need to do here. Exercise 2. It's going to be the same thing, except instead of a linear model, we're going to be using a polynomial data model. So you've got a constant plus something times x plus something times x squared, just like the second thing we did. Exercise 3. You're going to do the same thing, except we're going to go up to cubic. Exercise 4. You're going to do the same thing, except it's going to be exponential. And I'm not sure where your homework will cut off because I know this won't be there. But is exercise 5 still there? Okay, so exercise 5 is basically you've done what? 1 through 4, and you want to pick the one you like. Pick the one you think is best and write down why you think it's best. And then using the one you chose here, input these numbers and see how close you get. All right. So it's pretty straightforward. Do the method we've been doing all lab for linear, quadratic, cubic, and exponential. Pick the one you like and explain why. And then use it on these inputs. And you'll notice that these inputs are not included in the original. And see how close you get. So if you put input 12 and you get like 27.8, you're off by 6.6. So could be bad, could be not bad. Depends. Okay, anybody got any questions? Or I suppose anybody have any questions? All right, well, if not, that's it. Got a lot shorter than this morning because I went through everything else. Okay, I've got office hours tomorrow, and I will see you all on Wednesday.